Okay, website midterm 1. Okay, so this afternoon we are going to start our discussion of circular motion, and this is basically what's referred to as circular motion in a plane when something is moving in a circle on a flat surface. Okay, for example, when a car is going around a roundabout, so the roundabout is flat, but you've got something moving around the roundabout like that. So basically, that's what you're talking about here. We're talking about circular motion in a plane. So we have to basically, there's a way of describing circular motion, but before we go to that bit, you have to understand that many of the things which we have come to depend on, for example, cars, buses, all these devices which make life very good and easy, they work because there's something which is turning. In this case, when it comes to vehicles and transport, it's the tires which are turning. So it's these tires turning which cause the bus to move forward in a straight line. So basically, that's a connection there. When it comes to circular motion, why are we looking at circular motion? It turns out that circular motion is actually how you produce motion in a straight line. If the wheels of a car are turning round, that's how a car moves forward, and that's how a car moves backwards, whether it's going forward or in reverse. And this allows us to go around quickly. Recently, we had a problem with traffic. I think most of Lusaka had problems with traffic. So in some places, roundabouts have been created. So in case where you're going around a roundabout, you need a roundabout to decongest traffic. Other applications which require circular motion is, I think, life itself. Life itself, if we were not going around in a circle, if our planet was not going around the sun, it was just seated there, then our planet life wouldn't be possible on Earth. But throughout the year, the Earth is constantly moving in a circle around the sun. The Earth also carries out two types of motions. Apart from going around in a circle in the sun, it also spins around its axis. The spinning of the Earth around its axis and also the tilt which it has, which it makes with the North Pole, the tilting of the Earth, that's what makes seasons possible. So you end up having rain season, winter, summer, like right now we're in winter, and all these things. There are other things which require circular motion, for example, satellite TV and also internet. At some point, internet isn't even up to this point. Internet is still delivered by satellite. And also, if you want to watch your favorite shows on DSTV and everything else, you need a satellite dish which is going to connect you to a satellite which is moving around the Earth, like that. There are other machines which also require the use things to turn around. For example, right now, I'm using a computer and my computer has got a hard disk. So for a hard disk to work somewhere, something has to be spinning. Okay? So we use hard disks to store data, to store our movies and store things, but part of a hard disk, somewhere something has to be turning. And that's basically how these things work. So whether it is the Earth supporting life, the Earth has to go around in a circle somewhere. It has to go around the sun. That's how you end up with 1 year, 2 years, and I don't know how many years people have. So basically those years tell you basically how many times the Earth has gone around the sun since we were born. If you are 22, it means that since the time you were born, the Earth has gone around the sun 22 times. Okay? So you've looked at how cars work. You need tires. Those tires have to turn. If a tire stops turning, your vehicle stops moving. We have got roundabouts. Roundabouts, that's how we end up with modern cities, with roundabouts making traffic easy. The Earth itself has to go around the sun. That takes 1 year. Then also, every day you've got day and night. So the day and night is possible because the Earth is spinning. so that you can sleep also, because if the earth was not spinning on its axis, you would just have one part of the planet to be in the sun, the other part of the planet will be in darkness. So clearly, I think it would be very difficult for those people whose part was always in the sun to sleep. You wouldn't be able to sleep. So basically, you end up dying and stuff like that. Or, yeah, most likely that's what would happen. You also have the moon going around the sun, and the moon is also important for that bit. I've talked about satellites, I've talked about computer hard disks. In our kitchen, in hospitals, there are machines called magnetic resonance imaging, MRIs. These machines are used for getting images of a patient, so that doctors can quickly see whether it's a brain scan or whatever part they're scanning, so that pictures can quickly see what's wrong with the patient. Somewhere in the MRI, there's stuff which is turning. There are pieces of the MRI which is turning, and that's how it ends up making pictures of the patient. In our kitchens, you have got mixers and blenders. These all work by turning things. So basically, there is a lot which can be done if you are able to manipulate how things turn. There is also another thing which I've not put here, for example, a concrete mixer. For a concrete mixer to work, it has to turn. These concrete trucks, which we use for the concrete we use for building, for modern construction today, if you're building a shopping mall, or you're building an upstairs house or some apartment block, if you're going to build something which is modern, you need concrete. And concrete, usually these days people stopped making concrete on site, so they have to bring the concrete from somewhere, from some plant which makes a concrete, and it has to be transported using a truck. And this truck, if you see this truck, these concrete trucks, there is a container which is always turning. So basically, yeah, when it comes to things turning round and round in circles, it's very, very important. Whether something is going around in a circle, like the sun going around the planet, or whether something is spinning on its own axis, like in the case of a concrete mixer, or an MRI, or blenders, it's still motion in a circle. And these things have allowed, basically, rotational motion has allowed us to develop new technologies and to enjoy a lot of conveniences in life. So the topic we're basically looking at is, it's very, very important. Since you guys are trying to be doctors, I've mentioned an example of one of the machines in hospitals, MRI scanners, which use rotation. There is also other machines like centrifuges in hospitals. These centrifuges are used for separating blood samples. You spin a sample, then things get separated. Then eventually, maybe a technician or a biochemist will do whatever chemistry they want to do, and it helps with diagnosing disease. So you should have a good idea of what this is, and that's basically what we are trying to do. So what are we up to today? So basically, we are interested in seeing how we describe circular motion. We have seen how to describe motion in straight line. When it comes to motion in straight line, we have seen that we can describe motion in straight line using something called distance. Also, we can use displacement. Then you have seen how fast, if you're covering the distance, you can use velocity and what's this speed. We have also looked at acceleration. What acceleration is, that is when we're talking about motion in a straight line. Then we went further, we came up with some equations of motion, which we use for describing motion in a straight line. And basically, what I'm trying to say is that that's how we describe motion in a straight line, but there's also a similar thing which we can do with circular motion. We can apply something which is a description, which is, just a minute. So we can come up with a way of describing circular motion just the same way we did with motion in a straight line. And like one of the examples I gave, for a car to move, the tires have to move. For a car to cover a particular distance, if you want to drive 5 kilometers in a straight line or a kilometer in a straight line, those tires have to move. So the amount of turning which the tires are doing is related to how much distance you're going to cover. So if the tires turn a lot, then you cover more distance. If the tires turn faster, again you cover more distance in a straight line. So there's actually, the other thing I want to bring to your attention is that there is a relationship between circular motion and motion in a straight line. So what we're going to do is we want to see how we describe circular motion, almost similar to the same way with what we did with straight line motion, and you're going to move on from there. Then after that, once we see how we describe circular motion, then the next bit will be to find out what causes circular motion. Okay, so when something is turning, when you're moving in a circle, how much distance you move in a circle is what is referred to as angular distance. If you cover a particular distance as you're moving in a circle, that is what we refer to as angular distance. How fast you are while you're moving in a circle, that is what is referred to as angular velocity. And how fast the velocity or the angular velocity, how fast something is spinning or turning, that is what is referred to as angular acceleration. So basically, you notice that as much when we were moving in a straight line, the amount of distance you covered was called displacement. In this case, the amount of distance you cover as you are moving in a circle, that's what is called angular displacement. The amount of the velocity when you're moving in a straight line, how fast you're covering distance, that was referred to as velocity. In this case, how fast you're covering angular displacement, that's what you're calling angular velocity. Then how fast the velocity is changing, that's what we called acceleration. In this case, how fast the velocity is changing, that is what is called angular acceleration. So we're going to see how these terms are described. And the other thing is we'll need to be able to work out problems, of course, related to uniform accelerated motion in a circle. And yeah, so for starters, how do we describe circular motion? Well, we'll start with angular displacement. What do we mean by angular displacement? Okay, now if you have a car which is going around a roundabout, let's say you have a car, okay, this car has got tires, fine, then this car is going to go around a roundabout. This roundabout has got a certain length. Since a car has to go around it, so it has got a certain length or circumference, and you're going to call the length of the roundabout S. We're going to denote the length of the roundabout S, and of course the roundabout has got a certain radius R. So if the length of the roundabout is S and the radius of the roundabout which the car is going around is R, we know that a roundabout is a circle. Usually roundabouts are circles. So if the length of the circle is S and the radius of the roundabout is R, then there is a relationship between the length of the roundabout and the radius. And that relationship is given by this, which is the circumference of the roundabout. S is equals to 2 pi r. This 2 pi r is the circumference of a circle of radius r. So if you've got a circle of radius r, then this radius you multiply it by 2 pi, then you're going to get S. Are we clear? On this bit? Are we clear with this relationship? S is equal to 2 pi r.
Yes.
This is just from mathematics. From your grade 11 mathematics, I think, that if you've got a circle of radius r, then the length of this circle is the circumference. And we are saying here that the circumference is S. The reason is, you can get a roundabout, you can cut it, then you can stretch it into a straight line. If you get the roundabout, you cut it as a point, then you can imagine you stretch the roundabout into a straight line. The length of distance you're going to cover is going to be S. So this is showing that there's a connection between how much you're going to move in a circle and how you move in a straight line through the circumference. S is the distance you're going to move in meters, then 2 pi is something, we're going to see what it is, then r here. Now, this r here is the radius of the circle. The r is the radius of the circle. S is the distance, is the length of the roundabout. But there is this bit here. There is this 2 pi. You've seen the 2 pi? Have we seen the 2 pi?
Yes, sir.
This 2 pi is what is referred to as angular distance. The 2 pi is what is referred to as angular distance. And this angular distance is an angle. If you still remember some of your mathematics, 2 pi is actually equals to 360 degrees. So 2 pi is an angle. So basically, when you're talking about circular motion, you are measuring distance in terms of angles. Are we clear? You are measuring distance in terms of angles. But as you can see here, we have not used 360 degrees. What this formula uses is 2 pi. 2 pi is also an angle, but it's an angle which is measured in units of radians. So there are two units you can use for measuring angles. You can use degrees. You can also use something called radians. So 2 pi radians is equals to 360 degrees. So this 2 pi, which you're seeing here, this 2 pi is actually an angle. And this angle is actually measuring distance. It's a physical quantity that is measuring distance in terms of angles. So this 2 pi is what is referred to as angular displacement. That's what we are talking about here. So this is distance you are covering in terms of angles. And we denote this angular displacement using the symbol theta. So in place of this 2 pi, we can write theta. So we can say it doesn't matter the amount, so that we can come up with from this 2 pi, s is equal to 2 pi r, we can come up with a relationship which is going to give us how much distance you are going to cover if you move in a circle of radius r through a particular angle. So the distance you're going to cover is in meters is equals to the angle, which is theta, in radians multiplied by radius. Here, s is equals to theta r. This is a relationship which gives you, this is a formula which gives you the relationship between the distance moved in a straight line, which is s, the angle through which you move, theta, multiplied by the radius. In circular motion, we measure distance in terms of angles. So you have moved 20 degrees, you move 45 degrees, you move 50 degrees, you move 90 degrees, you move a distance of 180 degrees. It can be anything, really. It only depends on how far you are. The actual distance in meters which you move depends on the radius of the circle. Are we clear? The actual distance s depends on the radius of the circle, because you have to multiply the angle theta in radians times the radius, how far you are from the center of the circle. Are we clear? We can come up with a formula which gives us theta, which is the angular displacement. So here we can divide both sides by r. If we divide both sides by r, we end up with this. Theta is equals to s, which is the line, the circumference of the circle, or whatever. It can be the circumference of the circle, or it can be the arc length of the circle. It doesn't matter, as long as it's some distance which is part of a circle. So theta is equals to s. S can be the circumference, or s can be the arc length of a circle, divided by the radius of that circle or arc length. So if you go around a part of a circle, whether it's an arc or whatever it is, a roundabout, when you go around the whole roundabout, then you divide this roundabout. It doesn't matter how many meters you go around the roundabout. Then you divide by the radius of the roundabout. Then what you're going to get is what is referred to as angular displacement. This angular displacement is measured in units of radians. And in short, the short way of radians is rad. Now, there is a relationship, like I've said, between radians and degrees, and that is 360 degrees is equal to 2 pi radians. Also, if you go around a circle once, we call that a revolution. So 1 revolution is equal to 360 degrees, and this is also equals to 2 pi radians. So there are 3. There's one official unit, one SI unit for measuring angular displacement, that is a radian, but there are also 2 other units. There's a degrees, and there's also revolutions for measuring angular displacement. Are we clear?
Yes.
So this is what is referred to as angular displacement. When you move in a straight line, the amount of distance you move in a straight line, we call that linear displacement. When you're moving in a circle, the amount of distance you move in terms of angles, if you move 20 degrees or 45 degrees or 90 degrees, that is what is referred to as angular displacement. And angular displacement is measured in radians, and of course radians are related to degrees. 2 pi radians is equal to 360 degrees, also equals to 1 revolution. So this is how we define distance in terms of a circle. Moving in a circle, we define distance in terms of angles, and this quantity which we're talking about, how much distance you've moved, this is what is referred to as angular displacement. Okay. So, for example, we want to find the angular displacement. Here we have an example of a bob. Here, where is that? We have got this. This is a bob swinging from a pendulum. So the length of the pendulum is 90 centimeters. Here, the length of this string is 90 centimeters, and this happens to be the radius because this bob, as you can see here, it's moving in a circular path. This is part of a circle. So if the bob covers a distance from here up to this point, the distance is 15 centimeters. That is the distance the bob has moved. And the radius of this circular path is 90 centimeters. Then you can find out how much this angle is. This angle is the distance which has been moved in a circle. This is what is referred to as angular displacement. So you can find out what the angular displacement is. So in our case, we know that angular displacement, theta, is equals to the distance s, which has been moved in meters or centimeters, divided by the radius of the circle in meters or centimeters. So in our case, the length of the pendulum is 90 centimeters. This 90 centimeters is the radius of the circular track. Then the arc length in which the pendulum moves is 15 centimeters. So we can find theta, which is the angular displacement. The angular displacement theta is equals to s divided by r, and s is the arc length is 15 centimeters divided by radius 90 centimeters. In this case, I'm not changing anything because I'm dividing. I divide centimeters by centimeters, so the centimeters will cancel out. Whether I change the 15 centimeters into meters or the 90 into meters, they'll still cancel out. So when you do this division, you're going to end up with 0.17. Now, since you are talking about angular distance, the units are going to be radians. So you end up with 0.17 radians. Are we clear?
Yes.
This is 0.17 radians. These radians, of course, you can change them also. You can change them into degrees using this relationship here. 360 degrees is equals to 2 pi radians. So this 0.17 radians, you can multiply it by times 360 degrees divided by 2 pi radians, then you get whatever this much is in degrees. Okay, so this relationship, this relationship which you have here, this you have to know. This is theta, angular displacement in radians, but you can change it into degrees using this relationship. You can also change it into revolutions, how many revolutions you have using this same relationship. 1 revolution is equal to 2 pi radians. 360 degrees is equal to 2 pi radians. So this relationship is very, very important for you to know, so that you can easily move from radians to degrees or revolutions. We, as people, we understand revolutions, we understand degrees better. Normally, we do not work in radians, but other things, for example, our formulas, they use radians because there is no mathematical formula which uses degrees. Everything works in radians. You multiply things in radians. Are we clear? So you always have to change your degrees into radians. You have to change your revolutions always into radians so that you can carry out these multiplications and stuff. So that's the first thing you need to be aware of. Always, if you're given an angular displacement which is in degrees, change it into radians. If you're given an angular displacement which is in the revolutions, change it into radians. The reason is because it's only by using radians that you can multiply distances with other things. The other thing we want to look at is your speed. How fast are you moving in a circle? Now, how fast you're moving in a circle is what's referred to as angular velocity. Now, we have seen, for example, the Earth. The Earth goes round the Sun once in 365 days. So the Earth goes around the Sun once per year. When the Earth goes around the Sun once, that is 1 revolution. That is angular displacement. That's 1 revolution. When it goes around the Sun once, that is what we call 1 year. In 1 year, the Earth goes around the Sun once. That is the distance it covers. That's 1 revolution. That 1 revolution is also equals to 2 pi radians. So you see, it doesn't matter. When you're talking about circular motion, it doesn't matter how far you are from the center of something. As long as you go around once, we call that a revolution, and that is equal to 2 pi radians, and that is equal to 360 degrees. The actual distance you cover as you go around the Sun once depends on how far you are from the Sun. Other planets like Venus and Mercury, they go around the Sun in a much shorter period of time. The reason is because they're closer to the Sun. So the distance they actually cover is less. Our planet covers a certain amount of distance. So the amount of angular distance you cover divided by how much time it takes you to cover this angular distance, this is what is referred to as angular velocity. Basically, angular velocity is a measure of how fast something or an object is going around a circular track, or how fast something is spinning. Angular velocity is a measure of how fast something, an object, is going around a circular track, or a measure of how fast an object is spinning. And how do we do this? So we have to divide the angular displacement, how much displacement you have covered, divided by the time, t. And this is what gives you angular displacement, angular velocity. And angular velocity is denoted by this letter which you have here. It looks like W, but it's not W. It is a Greek letter called omega. Are we clear?
Yes. Yes, sir.
Now, the units for angular displacement, we know they are radians. The units for time, they are still time, whether you're moving in a second or not, is still seconds. So the units for angular velocity are radians per second or rads per second. Okay. If you go around a circle once, the amount of angular if you go around the circle once, the amount of angular displacement you cover is 2 pi r. If you go around the circle once, your angular displacement is 2 pi r radians. Now, usually going around the circle is going to take you some time. The time it takes you to go around the circle, that is what's referred to as a period. The time it takes you to go around the circle has got a special name in physics. When you go around the circle once, we refer to that time as a period, and it's denoted by capital T. So if you go around, for example, in the case of Earth, you go around, when our planet goes around the sun once, the angular displacement is 2 pi radians. Then the time it takes our planet to go around the sun, that is 365 point, I don't know, is point half or something, or 25 point quarter days. Each day has got 24 hours times 60 hours, 60 minutes times 60 seconds. So basically, each day has got a certain amount of seconds. 24 times 60 times 60. That gives you the number of seconds which are in a day. That number of seconds which are in a day multiplied by 365 quarter days, that gives you how many seconds are in a year. So you can divide your 2 pi radians, which is the angular displacement, because our planet goes around the sun once, divided by how much time it takes, then it's going to give you how fast the planet is going around the sun. Okay. The other thing which I want to bring to your attention is, we have talked about the time it takes an object to go around the circle. That time is what is referred to as period. Now, there is another physical quantity which is related to period, and that is what is called frequency. Frequency is a measure of, basically, the frequency F, denoted F, tells you how many times an object goes around in a circle per second. How many times does an object go around in a circle in 1 second? If an object goes around in a circle 2 times or once per second, then the frequency is once. If an object or an event happens 2 times per second, then the frequency is 2 hertz. It's measured in hertz. And this frequency is basically related to the period like this. It's an inverse relationship. It's a reciprocal relationship. Frequency is equals to 1 over t. Like this. Frequency is equals to 1 over t. The more time it takes you to go around a circle, the less number of times you go around that circle. So if you are taking a small amount of time to go around a circle, then you're going to go around in that circle many times. But if you're taking longer and longer to go around the circle, then you're going to go around this circle a fewer number of times. Are we clear on what frequency is? Frequency is a measure how many times an object goes around a circle per second, in 1 second. And you can find out what the frequency is by finding out how much time it takes an object to go around a circle. if it takes you 1 minute to go around the circle, 1 minute is 60 seconds. So the frequency is going to be 1 divided by 60 seconds, and that's going to give you the frequency. It's going to give you how many times you are going to go around per second. So with this new information, we can now come back here. With the new information we have, we can now come back here. And frequency is measured in what's referred to as hertz. 1 hertz is just equals to 1 per second square, per second, 1 per second, 1 time per second. So this omega, which is the, what is, the angular velocity is equals to the displacement divided by the time. So if you are going round in a circle once, 1 revolution, then your angular displacement is going to be 2 pi. That's your angular displacement. But for you to go around the circle, you're going to require a certain amount of time. The time it takes you to go around the circle, that's what's referred to as the period. Then when you rewrite this, you end up writing it like this, 2 pi. Then you can write this as 1 over t. You see this bit here? You can write this as 1 over t. 2 pi, 1 over t. But 1 over t is this here. It's frequency. So you can also write your angular velocity to be equals to 2 pi f. 2 pi f. This expression here. 2 pi f. That's your angular velocity, 2 pi f. Your angular velocity, apart from being given as angular displacement divided by time, you can also get angular velocity as equals to 2 pi f. This is another expression you're supposed to know. This omega is your angular velocity. Angular velocity is equal to 2 pi f. F is the frequency, how many times you're going around the circle per second, or how many times something is happening per second. Are we clear? Are we clear?
Yes.
Okay. There is another way of working out something called average angular velocity. Remember what time is in physics. Time is an amount of time when something is happening. That's what we refer to as time, the duration when something is happening. So if, for example, when you start measuring something, you start measuring how much distance, the angle is theta I. That's your initial angular displacement, theta I. Then after, the angle is, after a certain amount of time t, the angle is now theta f, which is your final angular displacement. So here we are looking at a situation where you've got initial angular, you know the initial angular displacement, you also know the final angular displacement. So you know what the initial angle is, you know what the final angle is, and for you to move between an initial angle theta I and theta f, you know how much time it took. You can work out these, the difference between the final angle and minus the initial angle divided by the time. This is going to give you an average. There's another way of doing this where you add theta I plus theta f divided by 2. You also get yourself average angular speed, velocity. Are we clear? Are we clear? Any questions? I have an example here. Example number 2. A flywheel turns at 480 revolutions per minute. Compute the angular speed at any point on the wheel and the tangential speed 30 centimeters from the center. So basically, this which we have been given here, this is angular velocity. You can measure angular velocity also in terms, remember a revolution is one way of measuring angular displacement. So it also happens that you can measure angular velocity in terms of revolutions, how many revolutions are happening per minute. Are we clear? So this which we have here, 480 revolutions per minute, this is another unit for angular velocity. So we can change this angular velocity. Yeah, omega is equals to 480 rpm. So how do you do that? So that's going to be basically what this is 480 revolutions per minute. Then you can change this. Remember what a revolution is. A revolution is, one revolution is 2 pi radians. So we can change units, and a minute is 60 minutes, 60 seconds. So you can do this. 480 revolutions multiplied by 2 pi radians, 2 pi radians divided by revolution multiplied by 60 seconds times that, then you end up with this. So you can use some conversion factors, you end up with this. You can end up with 50.3 radians per second. So basically what I'm trying to show here is that these things, whether it's angular velocity or angular displacement, sometimes you'll be given the angular displacement in revolutions, sometimes they're given your angular displacement in degrees. You still have to change whether you're given your angular displacement in the revolutions or in degrees. You have to change it to radians. In this case, we are given angular velocity in terms of revolutions per minute. You cannot do your calculations in the revolutions per minute. You have to change this value of 480 revolutions per minute. You have to change it into radians per second, like this. It's only when you have this, you have changed you have changed the units of your angular velocity into radians per second, that you can do something useful about that. Are we clear on how we have done this? Changing revolutions per minute to radians per second. Is it clear? So you need to be able to do this. You need to be able to change this by using a conversion factor, change the revolutions into radians, change these minutes into seconds, then you do some multiplication, then you should end up with 50.3. I think next time when I go through these notes, I need to do a better rewrite. So once now that we have our what's this? Our radians per second, then there is this bit. Find the tangential speed. 30 centimeters. So tangential speed is basically, did I show something else? What other relationship did I skip? Okay. There is also another relationship between the velocity, which we know, velocity in a straight line with angular velocity. A relationship like this. Now, from here, remember what we have, what we started with. We started with this. Before I go, we started with this. S is equals to theta S is equals to theta multiplied by r. If I divide by t, S divided by t, if I divide by t on both sides, this S divided by t is going to give me v, which is the velocity in a straight line. Theta divided by t is going to give me omega. So the relationship which I have there, v is equals to omega r, comes from here. S divided by t, this side you divide it by t, so you end up with v equals to omega, this bit here. Theta, if you divide theta by t, you end up with this. So if you divide on both sides of an equation by the same thing, you haven't changed anything. But we come up with a new relationship, which is what we have here. Here, v is equals to r omega. So you can find out how much something is moving by multiplying the angular velocity times the radius. So in this case, our angular velocity is 50, is 50.3 radians per second, that one, multiplied by the radius. In this case, the radius is 30 centimeters, but you don't multiply using centimeters. You have to change your centimeters into meters, so that's going to be 0.3. So you end up with radius of 0.3 meters times an angular velocity of 50.3, so you end up with this velocity of 15.09, which is approximately just 15 meters per second. Please. So this is your tangential velocity, the velocity on the surface, on the tangent, straight line of a circle. So when you're in a circle of radius r, how much is your velocity in that circle at 30 centimeters? That's what the V is. Are we clear? Is it clear to everyone? What? Any questions?
Yes.
All right. Again, similar thing. A fan, example number 3, a fan turns at a rate of 900 revolutions per minute. Find the angular speed of any point on the blade. So the angular speed or the angular velocity. So basically, we are talking about omega. So we have got this speed you have been given in revolutions per minute, but we need this in radians per second. So that's going to be 900 RPM. That's going to be 900 revolutions divided by 1 minute. And if you carry out this calculation, you're going to end up with omega, which is equal to 92.2 radians per second. So this 900 RPM is just equivalent to 92.2 radians per second. Of course, the speed of any point away from the center of this fan, that's a radius. If a point is 20 centimeters away from there, so that this 20 centimeters is 20 centimeters is your radius. This is going to be 0.2 meters. So your velocity V is going to be equal to the radius, which is 0.2 meters, multiplied by the angular velocity, which is what you have here. So that's going to be, so your velocity V is going to be equal to 0.2 meters multiplied by 94.2 radians per second, and this is going to give you 18.8 meters. So this is how fast something is going to be. Now this relationship is basically telling you something, that your velocity also, if you're going to move around the circle, how far you are from the circle has got an effect. So your velocity depends on your angular velocity multiplied by the radius. So the more the radius, the more you move. You have to move. Okay. Any question on that bit? Now, sometimes, for example, if you've got a fan, if people still have fans in their houses, a fan has got those buttons which have got different colors of blue, light blue, a bit blue, which is going darker, and very, very dark blue. So depending on which button you press, the fan either rotates faster or it slows down. So when it comes to things which are rotating or moving, you can move, you can change your angular velocity. Whether you're moving around in a circle, for example, in the case of the planet Earth, the Earth goes around the sun at the same speed, really, at the same angular velocity. So it really goes around the sun at the same thing. It doesn't move faster, it doesn't move slower. But it's possible for you to move faster. Okay? It's possible for you to move faster, and it's possible for you to slow down. So if something is going to rotate faster or it's going to slow down, then we are talking about acceleration. Okay? So if the angular velocity increases over time or the angular velocity reduces over time, then we are talking about acceleration. And this acceleration is what is referred to as angular acceleration. Angular acceleration is denoted by alpha. So we denote angular acceleration using alpha, this alpha symbol. And how do we define angular acceleration? Angular acceleration is just a change in the angular velocity divided by how much time it takes to make that change. So you have your final angular velocity minus your initial angular velocity divided by how much time. Angular velocity is measured in radians per second, then you divide by the time, so you end up with rads per second squared. This formula, this expression, is a carbon copy of your acceleration formula. Acceleration itself is just in a straight line, but this one, now you're moving in a circle. Okay, so you can undergo angular acceleration whether you're moving in a circle or whether you're spinning on an axis. Like in the example I've given, an example of a fan. If you press a button on a fan which is much deep blue, your fan starts to rotate faster. So if something is rotating faster and faster and faster, it means that its angular velocity is increasing. The increase in angular velocity, by how much it has increased over a period of time, you can find out what's the final angular velocity, what is the initial angular velocity divided by the time it took to make these changes. Then that's going to give you what's referred to as angular acceleration. Are we clear? So angular acceleration just measures how fast things are, how fast the rotation is happening, the change in the rotation, how fast it's happening. Okay, let's have a look at an example. Example number 4, a wheel of 40 centimeters radius rotates on a stationary axle. So this is basically probably, it is uniformly sped up from rest to a speed of 900 revolutions per minute in a time of 20 seconds. So if it's coming from rest, then the number of revolutions per minute is 0. Then at the end of 20 seconds, the speed is 900 revolutions per minute. So you can see that in this case, from when it's at rest, the revolutions are 0 revolutions per minute. Then after 20 seconds, the revolutions are 900 revolutions per minute. So we can find out what is the angular acceleration in this case. So we know the radius, of course, the radius of the wheel is 40 centimeters, which we change to meters, 0.4. Then, of course, since it is coming from rests, 0 revolutions per minute is the same as 0 radians per second. Then our final velocity, omega f, is 900 revolutions per minute. So this omega f, 900 revolutions per minute, is 900 revolutions divided by 1 minute, which gives you this much, 94.2 radians per second. So we know our initial angular velocity is 0 radians per second. Our final angular velocity, omega f, is 92 radians per second. So now that we know the final angular velocity and initial angular velocity, we can use this expression to find out what is our angular acceleration. So when we do that, we're going to end up with alpha is equals to omega I minus omega f minus omega I divided by t. Omega f is 94.2 radians per second here, minus 0 radians per second divided by 20 seconds. So we end up with alpha is equals to 4.71 radians per second. This is the acceleration. How about the tangential acceleration? The tangential acceleration is this, the actual acceleration in meters per second. From this acceleration, alpha equals to 4.7 radians per second, you can also get the acceleration in straight line. The acceleration in straight line A is equals to r multiplied by alpha. A is equals to r multiplied by alpha, and that's going to be radius 0.4 meters per second multiplied by alpha, this 4.7 radians per second squared. So you get yourself acceleration of 1.9 meters per second squared. So what I've shown here with this formula here is the relationship between the acceleration when you're moving in a straight line and the acceleration when something is moving in a circle. There is a relationship. The acceleration in a straight line is related to the acceleration in a circle with this through this formula. Also, when you come up here, what did you show here? The velocity in a straight line is related to the velocity of an object moving in a circle, like with this through this expression, v is equals to rw or r omega. Then also, last but not least, s, which is the distance in a straight line, s in a straight line is related to the angular distance multiplied by r. So you can see this relationship. The straight line distance related to angular distance. Straight line velocity, linear velocity related to angular velocity. Straight line acceleration related to angular acceleration through r, the radius. Okay, any questions? Those relationships allow you to move between circular motion and angular motion. Between the two motions, you can move. Either you can look at the problem of a car moving in a straight line, you can look at it as a car moving in a straight line, or you can also look at it in terms of how the tires are turning. Any question? We've come to the end. For today's class. Are there any questions? Okay, if there are no questions, we'll stop here. The recording is going to be made available on YouTube. Yes.
Excuse me, sir.
Yes. Go ahead and ask. Okay, there's no question forthcoming, so stop.